Okay, let's get going. Thanks for joining. Share my screen. We'll be looking at a couple of notebooks for the second HuggingFace diffusers discussion, or second unit, if you will. And basic things here that he covers are how to use a pre-trained model rather than training the model ourselves from scratch, and also how to guide the model to do different things, including guiding it using text and guiding it using images. So I think that's we'll be looking at today. These are things we have obviously looked at previously, but this is using the diffusers library and the pre-trained models that exist in the library. So for loading a pre-trained pipeline, we just actually call a DDPM pipeline, and there's a list of these different models on HuggingFace that you can find. It takes a little bit of a searching, but for example, there's a DDPM-based celebrity headshots trained in 256 by 256 images. Once you grab that particular model, which is a pre-trained model, which uses the DDPM or method for training, then you can generate image from it or images from it, and it's as simply as calling, or we've seen the use of the call from the class, so it just means we get the images from the image pipe, and the pipe is essentially this pipeline, which is a pre-trained model, and it generates a nice image. A lot of clarity, and it's pretty good. But the generation process, as you can see, takes the full 1,000 steps of DDPM. And that's slow because you have to go through the process of 1,000 steps, starting at 0 and going all the way to 1,000. And in order to avoid that and to speed up the sampling, we've seen the usage of DDIM, which is the denoising diffusion implicit models. And so there, what he does is to show from the diffusers library, you could potentially grab a scheduler, and this time you grab the scheduler from the DDIM, the same model, but trained, or you use the DDIM scheduler, and you set the number of inference steps to 40. So this has been reduced by almost 25x, and instead of using 1,000 steps, you now can use 40 steps, and these are the various time steps, and you're jumping by 25 of the original DDPM steps, each of the DDIM scheduler time steps. And then he just says, let's create 4 random images and run through the sampling loop. So you start off with noise, and then go through the denoising process using the scheduler, and in this case, the DDIM scheduler. And what's nice is he also, I think, shows, and this is a nice illustration of how when you try to predict and took, I think we've seen this before, but again, it's good to orient ourselves that what this left side is just a noise. 4 images, so there are 4 image or 4 noised, fully noised image values here. And from that, if we were to predict X0 at step 0 of your denoising process, what does the X0 look like? And you can see that they aren't very great. And this also, I think, illustrates what has been tried to explain multiple times, which is this denoising diffusion, it's an iterative refinement process. So you predict X0, but then you use kind of an intermediate value and you go back and add noise to it, and then you redo the prediction. So that's what this particular steps explain really well by having these the noise and the denoised images. So if you were to predict X0 at step 0, this is what you would get. But then you take 10 steps. Remember, these are 10 of these steps. So you'll be 6, 9, you'll be at 750. When you do that, then these are the X0 predictions. So you can see it's a lot better X0s than what you predicted at step 0. Then at step 20, you can see that the images are beginning to emerge even in the noise state. But then when you predict based off step 20, if you predict X0, then these are the images. And then at step 30, you predict them. And then at step 40, which is kind of, or step 39, because step 40 is the actual X0 step. So at that point, you can see that the images are pretty clear and quite good. So this is where, this illustrates what you described, that the initial predictions are not great, but as the process goes on, you begin to refine what you get. And this is, again, I haven't gone through this code, but I just kind of added it here by using the question mark scheduler step. So you can go through it at your convenience and kind of figure out what is what are the steps that happen. And, it actually uses the DDIM formulas and papers and goes through each of like a dozen or 8 steps to provide the results of the sampling, which is kind of what we are seeing here. But this is the code that generates these images, process, if you will. And this is where the commentary that you've seen before of, the direction pointing to x of t or x of t minus 1 comes in. And that's the reason that each time you refine, you're getting a much better prediction of X0 than what you got at step 0. That's kind of a nice illustration of the denoising diffusion process using the DDIM scheduler. Excuse me. Then he also says you can just make the scheduler part of the image pipe. That is, you can use this scheduler with our original image pipe that we had created, which is actually the image pipe used the DDPM pipeline. But he says you can now, which is kind of interesting because I would that you would have had to have used this scheduler for the same scheduler for denoising that you use for noising it. But it turns out, at least from this example, it seems like that's not the case, that if you have a model trained on both, you can use the scheduler that you've created and make that the DDIM make the DDIM scheduler the new scheduler for the DDPM pipeline and generate images from that. And that way you're speeding up the pre-trained DDPM model and produce a fairly good. So the net effect of this, I think, these several steps is to illustrate that you can use a pre-trained model, how to use a pre-trained model, also how to kind of modulate the scheduler and how to use a DDIM scheduler. Now, maybe interesting, I haven't looked at this yet, but an interesting comment would be, we saw this paper I posted on Slack that now from Google Brain, I believe it was, that tries to produce images in 4 steps. And the question is, have they already created on HuggingFace scheduler corresponding to that paper? And if that's the case, can we generate uh, the denoised images in 4 steps instead of even in 40 steps? I haven't looked into that, but that would be an interesting thing. The next thing we look at is how to fine tune. There are some interesting data sets and interesting examples of this that people have done. One, I think, example that he points to is this, where people have created Pokemon images with various faces of famous people and so on and so forth. And I think this one even has a notebook that you can try working with on data sets and so on and so forth. But in this case, we do something simpler. You take the vintage faces data set, and he doesn't use the anim faces. He uses a butterflies data set that we had seen in Unit 1 and fine-tunes it, fine-tunes the pre-trained model. The model is being pre-trained on the faces data set, and then it fine-tunes it on the butterflies data set. So you get the butterfly data set, kind of just print 2 images. You see the various images of butterflies, and then he kind of illustrates a couple of different ways of doing the fine-tuning. One, where you set or a faster way to do it, which doesn't use as much memory, and then a slower way to do it, which uses a lot more memory. And I'm, personally, I haven't fully grasped why the 2 methods are fundamentally different, and he kind of explains it, simply saying that, in one case, the derivatives pass through the unit model, in the other case, they don't. But I'd like to explore that a little more in terms of the equations and what really happens and so on. But the simple thing he does is for a couple of epochs, and the other technique which we've seen before, and I believe we saw this even in the Fast AI course, but nice explanation, simple way to gradient accumulate, whereby by doing the gradient accumulation, what you're doing is essentially increasing the batch size without effectively increasing batch size, without actually increasing the batch size. And that's something else that we see, besides the fact that he does the fine-tuning in 2 different ways. So the first way, this is just for the training loop. We update the weights of the pre-trained model by kind of taking the pipelines unit and tweak the parameters. So by this, what we are doing is the unit parameters, which have been originally pre-trained, we kind of tweak them a little bit because we just train for a couple of parameters, for a couple of epochs. Sorry. We train that, add the noise, do the same thing as what we would do in a traditional training steps. We just use MSE loss for this, but do it for a couple of epochs. And here's where the gradient accumulation piece comes in. And he says, you can see how simple the code is. Basically, if whenever your step is, whenever you take 2 steps, but that step plus 1% gradient accumulation is 0. I mean, for every second step, you step the optimizer and you zero the grad, so that you accumulate the gradients for 2 steps before you actually apply them, if you will. And he says, hey, we're just training for 2 epochs, so it's kind of fairly noisy loss signal. And we're only working with 4 examples at random noise levels for each step. This is not great for training. And so one way to fix that is to use an extremely low learning rate. And that in turn, what it does is to reduce the step size for each step, thereby reducing the noisiness. But it would be even better if we can find some way to get the same benefit as using a large batch size, but we do not want to use a large batch size because of memory constraints. So how can we kind of sidestep the memory constraints while effectively increasing batch size? And that's where gradient accumulation comes in. What happens is if we call loss dot backward multiple times, that means it will be accumulating the noise. Remember that in PyTorch, the loss keeps getting added. That's the reason that we do the zero grad in the optimizer. So if we don't do that until we take a couple of steps, then what happens is the signal from as many steps we take before we take a step with the optimizer, all those gradients will get added. And so that effectively reduces the number of steps. So in effect, it's as if we have increased the batch size, but practically we are still using the smaller batch size. We're just playing with the frequency of updates to the gradients. That's the gradient accumulation. And the whole accelerate library makes this easy as well. But it says, hey, let's look at the actual way it's implemented from scratch, and you can see that it's just a couple of lines of code. So it's not that complicated to do. And this is a useful technique in all cases where the GPU is memory constrained. Right? And so he just says if you just look at the loss when you do this kind of fine tuning, it's not a very good indicator of progress. The reason being that the loss doesn't change a whole lot. So for example, when he does this and his own stored weights and biases image, you can see that the loss is pretty flat. It doesn't really go down a whole lot. Maybe a little bit at the beginning, but then it kind of bounces along, as you can see. So given that that's the case, is that what we should actually do to see whether our fine tuning is having any practical effect on the model and what it generates as the output, we should probably generate some samples occasionally to visually examine the performance as the model trains. Because otherwise, the loss is not a good indicator. Usually we just monitor the loss and say, oh yeah, we got a nice training going on, but that's not something that gives us a good indication when we fine tune a pre-trained diffusion model. So you log the things like the loss, but it's more important to generate samples and then look at them. So he has created a fine-tuned model.py that takes the training code and adds my minimum logging functionality. And you can see the logs from one training run, which is what we saw. I think maybe this is %% or something and debug why the line magic doesn't work. It's probably we've had success running this notebook, Mayank or Emily or Yuri.
Yeah, I had success here, but I wasn't able to execute the whole of the notebook because of the GPU issues. The VRAM of the GPU was a bit less here on my machine.
I see. Were you able to run this cell though, or did it crash before you got here?
I was able to run this cell. This cell signifies the weights and biases training script.
Yeah, of his. But I was just curious because for some reason it says time magic function is not found. So I was curious whether this is %. Sometimes I've seen %% used.
On my local machine, this works.
Okay, interesting. Okay, and then generating some images with this model, we can see that once you pre-train with the butterflies and then you sample, you can see the strangeness. Although, you know, a couple of images, it's kind of interesting. This phase is pretty much remained untouched. A little more changes here, but it's kind of trying to bring in whatever you deem to be butterfly concepts into its the unit model, thereby creating kind of butterfly-ish effects to the output of the model trained on faces. So, and this is where if you were to do it instead of with butterflies, with say the anime faces, you could probably get anime versions of the faces, if you will. That's where he says that, you know, this is not a very precise technique. It's pretty unpredictable. So you have to do it for maybe a lot more number of epochs, and then we'll begin to see butterflies instead of faces. But playing with various parameters is probably the way to kind of figure out like very short, very long, varying the learning rate, and all these different types of techniques. Now, he then uses the same model, that pre-trained model, which has been trained on the face images, the Google model that we've been working with so far, and then uses the WikiArt demo model to kind of fine-tune. And WikiArt is just a model that's trained on Wikipedia art images. So this one I was able to run because, and I had to use a V100 as mine points out, and he says it in the notebook as well. You'll need more GPU memory to do this part of the code. Again, he just saves the pre-trained model. As we've seen before, that basically means that the JSON file for the model index and then the scheduler and the unit are saved. And then you just kind of upload a locally saved pipeline to the hub. So this is just an illustration of how you upload a TPM. I just labeled the model this way, and you can then load it. It's just pre-trained celebrity models fine-tuned on the butterflies data set. You could, this is something where it'd be more interesting, I think, if it was, for example, fine-tuned on the anime data set and maybe more than 2 epochs, but I didn't want to spend a lot of my GPU hours doing this. Then that's the closure of just an illustration of how to fine-tune a pre-trained model. And here, what he does then is to show that if you take a model which is trained on the Elson bedrooms dataset, this is the final couple of notebooks of Jeremy Howard's course as well, where he trains a model on the Elson bedrooms, where we did it ourselves. But again, the Elson bedrooms dataset is humongous. Thankfully, in this case, John has actually done that already, and then fine-tune 1 epoch on the WikiArt dataset. And he says you can skip the cell and use the faces, but I actually utilized the cell, so I ran it. In this case, again, he kind of changes the scheduler. He uses the DDPM pipeline, but then uses the DDIM scheduler, so you can get a faster prediction of 40 steps. And then kind of you can view the model. There's a pre-trained model, which a pre-trained, actually the model is a model which is trained on Elson bedrooms and fine-tuned on the WikiArt dataset. So it's not just a pre-trained model, it's actually a pre-trained and fine-tuned model. Pre-trained on the Elson bedroom, fine-tuned on the WikiArt. And you can see that the WikiArt has had more of an influence here, and you can see, you know, some images which are just plots, if you will, or these seem more like color splotches than anything else. And as he says, it's often hard to tell whether fine-tuning is working. This is the reason he was saying that just observing the loss is not good enough. Also, what does good performance mean? And these are interesting things that you need to kind of play with variety of parameters before you can get to what level of control you get by varying the parameters. And he talks about this blog post that I had shared or shown as well, which is Lambda Lab guys had trained Pokemons on some faces of famous people and gotten Pokemon combined with this. And so the loss plot doesn't show much improvement in this same as before. Now, what if we wanted, this is just simple fine tuning, right? So you just take a pre-trained data set trained or elephant bedroom trained model and then fine tune it 1 or 2 or whatever number of epochs on the VKR data set. But what if you wanted to have a little more control than what's you get by just fine tuning? Because as you saw, as we have seen so far, fine tuning isn't a very controllable process. It seems fairly random of what we get as an output. So here, one way to do this is to control it through changing the loss function. So some measure that we'd like to minimize is by controlling the loss function. And one of the ways he shows is, let's choose specific colors as the output that we would like to get, and then compare the pixels of the image to that the fine-tuning process is generating to what our desired output should be. Now, his default that he uses is a teal color, and I changed the teal color to azure blue after finding out what the code, RGB code for azure blue is. This is the RGB code for teal, and you can see that teal is mostly green with very little R and what is a middle blue, right? So that's what 0.1, 0.9, 0.5 is, whereas an azure blue is again very little red and middling green and mostly blue. So I just did that and create a new version. And here's the 2 versions that I mentioned of how he does it. In the faster version, he just kind of sets the required get true later, whereas in the slower and more memory hogged version, he sets required get to true at the very beginning itself. And here are the steps: create a new version with required get, calculate the denoised version, which is the x0, feed the predicted x0 through our loss function, which is, remember, the MSE, so that the color matches, and find the gradient of this loss function with respect to x, and use this conditioning gradient, and that's why this is conditional guidance, if you will, and to modify the x before we go through the scheduler step. Right? So that's the way in which we guide the model or push the model in the direction that we would like the output to be in. So that's what this talks about, using the guidance function. So instead of just fine-tuning, we additionally guide the model in the direction that we would like. And then there are 2 variants that I mentioned. The first one, we set required grad and x after we get our noise prediction from the unit. So the unit is, we don't go through the unit in the reverse direction because we kind of go through it. We set the required grad to be true after we get the noise prediction. And in the second case, what we do is set the required grad right at the beginning so that the gradients have to go through the unit as well, which obviously, given the size of the unit model and all the stuff that is done there, it would require a lot more memory because you would need to store the gradients of all of the layers that we saw that are used in building the unit. So the first method is much more memory efficient because they don't have to trace, we don't have to trace the gradients through the diffusion model, but obviously it will give a less accurate gradient, right? Because your model, it's almost like freezing a portion of the model and just allowing the gradients to change on fraction of it. The second, we said require grad on X first and then feed it to the unit and calculate the predictor. So there we see, this is the, I was just also curious about what the scale model input does, and this is the code for how the scaling happens, if you will. And then go through the shortcut method. So here you see that he sets, first of all, the guidance scale to be 40, and he talks about weighting it to 5 and 100. I think, unfortunately, when I ran the notebook, I should have also done this, but I just changed it to, I ran once with 40 and once with 100. Probably should have tried 5 as well to see what effect it has on the guidance. Then we take a random X, prepare the model input, and predict the noise, then set the required grad to true. So we've kind of gone through this unit model already and then set the required grad to true, and then use the scheduler to step and use our loss, which is an MSV loss, where the color loss that is defined here, and the color loss is where we use the target color and make it such that the error is the absolute value between the images and the target, and then take the mean of it. So what we are doing by doing this is the mean absolute difference between the image pixel and the target color shaped in the same size as the image is what we are using as the guidance. This is how we push the model to generate closer to this color output from the fine-tuning results. So when you do that with 40, you see this kind of an effect. And you can see that a lot of azure blue or blue color is shown here to just illustrate the same thing when he does it using the teal color. You can see the images that are being generated are much more greenish. And what I did was change it to azure blue just to show you the difference. You can see that there's a lot more blue. The other thing, as I said, is I also changed it to 100 and reran it. When you change it to 100, what you're telling this process to do is heavily weight the color aspect. So you're guiding it aggressively, quote unquote. Therefore, you're telling the model to push it all the way such that the results are much more closer to the color output that you want. And when you do that to the extreme extent, like by setting it to 100, you can see what you get is pretty much azure blue. You pretty much told the model that just generate. So it doesn't do anything else other than generate azure blue color, so which is somewhat pointless. But that's why I also felt that I should have played with it to see 5 and see when you guide it very less, then what effect it has. Somewhat of an intermediate value is 40, which is, you can see what that does. So that's one way to guide the model, is playing with the color values and then setting the loss. But the principle is more general than that. And then obviously he also does the second option. And this is probably the reason why Mike was saying he was having trouble. You need double the GPU RAM to run this more complex process whereby you are actually setting the requires Grad to do right at the beginning before even predicting. And that means that all the gradients will have to flow through the UNet as well. And that's the reason that the demand for the GPU RAM is very significant. And you do that and you see that in this case, it's also not done 8 as before, again, saving memory. So you just use 4 images instead of 8 images, given the size of the images. And these are the 4 images that you get when it's 40. You could probably play again with changing the guidance law scale, try it as well. That would probably generate set of images. But you can see with same 40, what you get using this method versus 40 using first quicker method. And that, and in fact, as this exercise is something you just pick your favorite color, and as I showed you, I already did this. Edit the color gloss line, changed it from teal to azure blue, and this is the result you get. But this is kind of, in a way, guiding images, using images or using color of images. And you could instead use clip guidance, which is guidance using text. And there's a lot of notebooks, and even, I think, in this is clip related, what's clip, and he in a PGL course or whatever, and when I say he, I mean John Whitaker also has kind of done something where he has a series of lessons going through some of the stuff we have already seen, PyTorch, gradient descent, blah, blah, blah. But more interestingly, he talks about clip as a portion of his. This is exploring multiple modalities with clip. And then he also has this blog post about deep dive into OpenClip from OpenAI, which is also written by him. You can kind of go peruse that. And then there's the clip guided diffusion notebook, or code, I should say, notebook. Well, all of which you can go explore. And the basic approach is, things we have seen before of just, actually in this case, this particular part where the text is embedded, and from text we get an embedding, and then we combine it with the diffusion process. This step was not explained as part of the Fast AI course, so it may be something that you can pursue. If you're more interested, I definitely intend to do that. I haven't looked at it yet, but these are the couple of links that I pointed to. And then here you just kind of load a clip model. Here it uses a visual transformer, which is being pre-trained using by OpenAI, and then do some transforms, have a clip loss, and with a loss function defined, our guided sampling looks similar to the previous example. Instead of color loss, you now have a loss function where clip-based loss function. And you can now guide the model, the same model that we had. And here again, I changed what he had just to see the difference that I would get. He says red rose, still life, red flower painting as the parameters. So to show you what he gets when he does this, he does this, and he does prompts a model with a red flower painting, red rose, still life, and you see that he gets red, doesn't look like a rose, but a lot more red combined into the images. Remember that these are images, I think, which are Elfin with the art influence. That's what you get when you combine the red rose with it. Of course, they don't look like roses, and you can kind of have to play with the settings and so on to see or generate what you would consider the desired goal of what you're up to. Now, I wanted to change it to yellow rose to see what it did. And you can see that these look quite a bit different from his images. And you can see some butterfly-ish effects, and you can see a lot more yellow than what you see here. It definitely has had, and remember, we are no longer using the color loss, so it's all clip guidance. So the fact that you can use text to guide it to produce yellow color images versus red color images is pretty. And he also says that he's conditioning the scaling the conditioning gradient by the alpha bar square root. He does that here. You can see that the conditional gradient is scaled by alpha bar square root. And we've seen these plots before. The alpha bar square root is this guy, green. So it's this plot. And so he kind of says, hey, you can use no scaling at all, which would be this guy, flat, alpha bar scaling. So that would be the orange guy here. Alpha bar square root when you scale it by, then you do that. And then 1 minus alpha bar square root, which is of these. Right, this is low. Right, so these are various scheduling things you can play with, and this scheduling stuff is more an influence on the conditional gradient and how much of the conditional gradient you apply at what step of your scheduler. So that's what this does. And you can play with different schedules, guidance scales, any other tricks. It is clipping the gradients, which in some ranges another technique that people have used. And then also some code for clip guided diffusion. And that, I believe, was what this is, the clip guided diffusion. So you can use this code, shove it in a notebook and run it and see what the results you get. And then the last piece of this notebook, in fact, I wasn't able to run this. I don't know, Mike, whether you were able to produce a successful Grad.io demo, but again, this is fairly cool. I definitely want to get this to work, but again, I didn't want to spend too much time debugging it. But it seems to be more a problem with Grad.io than anything else. It just says initially when it installs, it failed to install a couple of things. Then I went back and installed them. Then eventually it gave me, when I started using Grad.io, it gave me this error, which is it has some trouble with importing the doc from the typing extensions. So I'm still in the process of debugging why that's the case. Don't know whether that's the Grad.io issue or typing extensions is something, it's a extensions on the typing module, and for some reason it doesn't like that. There is one idea I had for, I kind of manually installed Toledo, which is given here, that wasn't installed. And there's some incompatibility related issues. So I need to figure that out to get Grad.io working. But if that works, then you can kind of upload and create a simple demo on the web and host it on HuggingFace Spaces, where you can preload the model and of stuff like, you could potentially upload pictures of your own pet, create anime versions of it, and so on and so forth, and host on HuggingFace Spaces as well with friends. And he says that's also a duplicate. You can visit the demo space here, but unfortunately, if I recall, I did try that, but I was curious whether that would work, but if I remember correctly, that space that he talks about as a runtime error, I don't think that that works any longer. Color guided weekly ad diffusion space. You can just clone it, you can clone spaces, but the space that it points to is no longer functional. That he says by creating duplicate this space, then you can get a template that you can then create. But you know, this is more a final thing to share and show and tell, but the rest of it is where learning and the most fun stuff. Any questions on any of this stuff? Then I think these, by the way, are good links where the different models exist: spaces, bedrooms, cats, and then this is the WikiArt model. So these are interesting because if you want to kind of use pre-trained model and fine tune them, then these are the things that you would typically use. The reason you would use some of these is because otherwise you'll need 1,000 images of your own in order to have any significant effect in terms of fine tuning the model. And then you can use kind of guidance and stuff. So that's the first notebook on how to use pre-trained models, how to modify their schedulers using variety of new schedulers, also an ability to kind of fine-tune models using other data sets, and then subsequently kind of guiding it with images, guiding it with color guidance, guiding it with clip, which is more a textual guidance, and then finally uploading it, the whole thing onto HuggingFace spaces using Grad.io. Were you able to get to the Grad.io portion at all, Mayank, or did you just give up after your thing crashed?
Yeah, I wasn't able to reach the Grad.io portion here.
I was curious why. I mean, this has nothing to do with kind of anything diffusion related. It's more an import related issues having to do with typing extensions that it was based on that, or a Python related issue. So anyway, we'll figure this out. The next thing he does, which Jimmy had shown us as well, but it also is a good illustration of how you can do all of this without mini AI and just using PyTorch, is introducing a class conditional diffusion model. So remember that the thing we were, when we create a denoise diffusion model, what it creates is type if you're just using MNIST digits, for example. So whether the digit would be a 5 or a 6 or a 7, we have no control over if we just applied the denoise diffusion process. But what if we wanted control over that? What if we wanted to say, let's say, instead of generating a random number between 0 and 9, I want you to generate images of 5. And the corresponding example, if you were to use pets data set, would be, I want an image of a particular dog, for example, and variations of images of that dog, of the particular class, a poodle, say. But if we wanted that level of control, then what do we do? And this is how we get to that. And here, he's just using a very simple MNIST data set, but the methodology is the same if you were to do it for a much larger data set. Basically, you use a class label in addition to the time step and the image that you pass through the unit. And that is how you get back, and the class or images produced by the unit would then correspond to the class label that you send in as well. So you load the data set, you generate a bunch of images to see in, these are various numbers. And how do you create a class condition unit? So you take a standard unit 2D model, except you add additional input channels, map the class label, and we have seen this in gory detail in Demi's last few notebooks, where he showed us how to convert the time step into an embedding and then create the cosine and sine combinations and so on. We saw that. And then finally, he also had a small snippet in the notebook where he showed us, how do you class condition? And this is, if you will, a more elaborate explanation of the same thing. You just add a class label, you pass it through an embedding layer and create an embedding, combine the embedding, and combine here means concatenate as extra channels for the unit, so that your input now becomes the image class conditioning. Right? And feed this, which now has class embedding size plus 1 channels in total to the unit to get the final prediction. So he's just done it very simply by setting the class embedding size to 4. So this arbitrary, and he says you can explore it to just having it to be size 1, or it could be size 10 to match the number of. It doesn't really matter. It's just all you need is to create an embedding and to combine it with the image and the time step and pass it through the unit. And you could even do a simple one-hot encoding of the class label. And here's the implementation, here's the unit, but the unit now takes in 1 plus the class embedding size, right? So you need to kind of create additional input channels in order to allow you to do the class condition. Once you've done that, you just go through the same process and you kind of create the class labels, pass it through the embedding layer to create the class conditioning, and reshape the class conditioning to the shape of what you want, which is the X shape is BS12828, and so now class conditioning is BS42828. 4 comes from the fact that he has created the class embedding size to be 4. And that's why it's 42828. And then the net input is just combination of X and class conditioning. And then you pass in the input and the time step. So in effect, what you're doing, and if you saw that in the way Jeremy had done it, he did it slightly differently. He passed in X, the time step, and the class conditioning. And the class conditioning also, he coded it to the same size as the time step embedding, so that you could then concatenate all of them. And you can, so this just illustrates a slightly different way, but the net effect is to pass the embedding along with the time step and the image into your unit when it does the prediction. And then you train and sample. So previously, as you said, prediction is unit X and T. We'll now add the correct label as well. So now prediction becomes unit X, T, and the label, right? And at inference, we pass whatever labels we want. And if all is well, then the model should generate that match. That means if we want 5, we pass in 5. If we want 0, we pass in 0, and so on and so forth. So the training step is similar to what we did in Unit 1. And one difference, and this is something that Emily had asked a question about as well. I still haven't gotten to the bottom of fully understanding the math behind it, but there is an explanation for why predicting the noise is better than predicting the noised image. And here in this notebook, the training he uses the predicting the noise rather than predicting the noised image. In Unit 1, he used predicting the noise image. So here itself is a good kind of, if you will, good example. You could potentially create a notebook where you train using noised images or producing output of noised images, and you can run another training loop which uses predicting the noise, and then you can use denoising from both of them to see which produces better inference results. But of course, that doesn't tell you why it does that, which is the question that I asked last time. In pursuit of that, there are some explanations in one of the videos that was pointed to in Unit 1, but the math behind it is a little complicated. Then create a scheduler, do the training, but here you predict the noise versus predicting. So here the prediction is the X time steps and Y, and note that we pass in the labels Y. And the loss is this, do the backdrop, get that, and you can see that the training goes very smoothly. And once the training finishes, you can sample some images, but you pass in here the labels that you want. Here it just says create 8 images of my entire range 0 to 9. So you can see when you pass 0, it creates images of 0. And you can also see that not all of the images are the same. 1, 2, 3, 4. 4 is interesting. 5, 6, 7, 8, 9. 2 9s are interesting too. So this shows us how we can control the image that we want produced if we have classes that we know. And he says you can try this with fashion MNIST. We have already done that. Take the learning rate, batch size, number of epochs and stuff, and figure out which of what produces the best results. This is class conditioning, and what we were talking about previously though is guiding, which is not very precise. So that's why it's called guiding, but in this case it's class conditioning. So here you can specify a class and it will generate images of that class. But in case of guidance, it's more like you're nudging the model. You can take a pre-trained model, you can fine-tune it, and then you can guide it. And depending on the loss function that you use, depending on the combination of loss functions, and then the heaviness with which you guide it, this is the factor of what we were using, 40 or 5 or 100. It will push our resulting output closer to what we desire or have a good mix of results. So that's kind of the different knobs that we can use to control either to a precise level or to a more coarse level the outputs that are generated. That's it. And as I pointed out, there are some interesting related documentation. I haven't had the time to go through these videos and blog posts that you can go through. There's also a link to variational autoencoders. That all of these are links that post a part of this and I kind of try to identify the various locations. You can see these are all the different models, if you will. You can see that the Google DDPM, and this, I don't think this is the one he used. I think he used DDPM Select AHQ 256, but this is EMA, which I believe is even better model. You can kind of, and the Google GDPM church is model, pre-trained model trained on church images. And so you can see this, you know, doggies and a whole lot of dog. So these show you what kind of pre-trained models you have that you can then use And these are all the various models in HuggingFace. And this is just the tutorials, how-to guides, conceptual guides, references on diffusers, library, understanding pipeline models and schedulers. You can just open them in Colab and use the different. What does the pipeline do? How do you schedule? How do you time steps, random noise, Then there's the whole pipeline section. And I think in the fourth and last lecture, we'll look at an audio version of a pipeline. But, you know, this is the generative autoencoding related stuff from the TGL course. By the way, I believe a friend of mine had also mentioned that John O. Whitaker is himself writing a book. I think it's be published sometime this year, but keep an eye out. He's writing a book about generative models, especially generative visual models. Hey, that's all I had for today. Any questions? Comments? Yeah, if there are any recent papers or accelerated diffusion, the last one I saw, I think I posted on Slack, was the 4-step. I haven't played with that or looked into it. But if you see anything else, and as you had also mentioned, it'd be interesting to just poke around and see what the progress has been in this space since when these HuggingFace diffusion class, which was end of last year, and even Jeremy's course, it ended in Q1 of this year. So it's been about 6-9 months. I don't know whether there's been tremendous progress or the same, or whether things have more interesting or so on. So if people are aware of it, post them to Slack and we'll look and see how things have changed. Okay, with that, thanks for joining, everybody. See you all next week.
Thank you.
Thank you.
Thanks.
Bye.